So we're going to look a little bit of the theory. If you have a hard time to think about the n, just think about n equals 3. How about that? And the 3, then you get the position at a particular time. The first theorem, we call it the principle of superposition. Means if you have n different solutions, each of them solve this. And then if you add all together with the different multiplications, it's still going to solve this. To make it simple, let's go this way. x1 c1 plus c2 x2. I just do 2 of them. If let x equal this, well, if assume these are the solution, you start with this equation be true. And the x2 prime, a x2. Of course, if you put the x prime, that will be c1 x1 prime, c2 x2 prime will equal to a times x, which is a times c1 x1, a c2 x2. I told you about not switching the positions of vectors or matrix. But doesn't matter. You can take this c1, c2 out because those are number. And then you take a c1, c2 out. That's x1, c2, ax2. Did you see it? And this equal this. And that one here equal this one. No, equal this one. So, of course, that's true. So this x, if you made the 2 of them, still solve the problem. So you can keep going. Doesn't matter what is the n. That's how many variables you have, how many equations you have, and the A is an n by n matrix. Typically, not always. If you have such a system, you are looking for n linearly independent, means very different solutions. And then you're going to combine them. Superposition literally means overlap, one add another, add another, add another. Give an example. If you have 3 equations in algebra, you expect 3 solutions, right? In here, you have 3 variables, and you're looking for 3 different functions to solve the problem. That's the same idea. And then you can add those 3 together. Well, I mentioned the one word called the linearly independent again. You know a little bit in the algebra component, not much. It's a related concept. We're going to consider the determinant of all those solutions. Remember, each solution itself is a vector function. A vector function, let's say n equals 3, your first one might be look like this. See, that's one solution. You have 3 functions. Well, if you have this determinant, I need to put all those 3 side by side. The first one is a column, 3 by 1. And the second one is another column, and all the way to the n column. And you can clearly see, if you put it side by side, this is a n by n matrix. The n by n matrix have a determinant. And this determinant has a name called Wronskian. It's a significant concept you're going to see in the next theorem. The next theorem says, A, if the Wronskian is not a zero function, not a zero function means at least one point is not zero. You can just check at the initial point, x at t equals 0. If that's not a 0, what's the premise? The premise is all the n solutions is called linear independent. And linear independent simply call this matrix x1, x2, xn, it has an inverse. That's why it's called non-singular. The inverse exists. When you solve an equation analytically, you need to take that inverse. No wonder you need to look at the determinant. You remember that? In algebra, if you want to find this inverse, this determinant cannot be 0, right? If you use the Gauss-Jordan algorithm, that's the denominator, cannot be 0. So Wronskian is a benchmark for you to check if your solution are linearly independent or not. Why is it important? It's the same as in the algebra. I said that you have a homogeneous equation, you have infinite many solutions, but you can just multiply 1, multiply 2, multiply 3, doesn't make any difference. Let me show you what I mean. ET, 2ET, 3ET, that's a solution. That's 1. If this is a solution by the superposition principle, twice over here, twice here, twice here, that's again another solution. You got a second one? No, that's the same one because they are dependent. Unless you get something significantly different, like e to the 2t, e to the 2t, 3e to the 2t, well, you know that's different. That's what the concept means, linearly independent. You need a significant difference. The second definition, other than the Wronskian, is called the fundamental solution matrix. I told you if you have n variables, you're looking for n linearly independent solution. If you got all the n, great. That means all other solutions, doesn't matter how different, they must be a linear combination of this. A linear combination means a supercompose, means overlap them, add them. Just like in the signal, how my voice is made. My voice is made by superimpose all different frequencies, and then you hear my voice. The same way, and you supercompose all those solutions, you get the so-called a general solution. That's another concept. A general solution will cover all solutions you need. Then the particular one really depends on the initial condition. If you have trouble, we're going to look at examples. So in case you did find this linear independent solution, how many? Got n of them, and then good news. You got this called the fundamental solution matrix, and your general solution will be look like this. And equivalently, you can write as this matrix, which is an n by n matrix, times a vector c. That's another way to write c1x1, c2x2, all the way down. It's still too complicated. Look at examples.